Okay, put this on. And we can talk about the solution of the midterm. How was it? How did it compare to the first exam? Harder, easier, about the same?
It was about the same, but I like that there were like 4 different questions that felt like roughly the same difficulty, rather than like 6 or 7 easy questions and 1 hard, like long question.
Yeah, what would be the point of distributing the difficulties like that, right?
I like the fact that it was not distributed differently, because that way, like, if all your eggs aren't kind of in one basket, you can kind of go in right on.
Okay. Well, I personally think they are fairly close, especially with a few questions. They're fairly close to the questions in the practice exam. It's just that instead of giving you A, B, and C, and you have to derive D, I give you B, C, and D, and you have to get back to A. So it's just changing the direction of the reasoning, but it's basically the same stuff. Okay. Such as question number 1. So question number 1 is, I would say, fairly close to question number 1 of the practice exam. Except in this case, I do not give you the probabilities. I gave you the observed probabilities of the errors, okay, the patterns that are received incorrectly, and then you have to work your way backwards to figure out what are the probabilities of errors. Okay, so it's different in that sense, but otherwise, there's a lot of similarity between the practice exam and this particular question. So the way to approach this one is, first of all, like any other exams, read the question very carefully. Via lab testing, it is determined that a transmission-receiver combination has errors. Specifically, there's one error rate of a 1 transmitted but received as a 0. Okay, so when a 1 is transmitted, there's a chance to receive as a 1 correctly, but there's also a chance that it may be received as a 0. And there's another error rate, okay, so the key here is these 2 error rates are different. Of a 0 transmitted but received as a 1. Furthermore, these error rates are completely independent, which means each time a bit is transmitted, the error rate depends only on that bit and no other bits transmitted before, which makes the analysis a bit easier because it's not context sensitive. It is observed that when 110 is transmitted, the other 4 3-bit sequences are not observed. So I only observe these 4. There's a chance of 0.576 that it is received as 110, which means it's received correctly. A chance of 0.016 that it is received as 101. A chance of 0.016 that is received as 011, and a chance of 0.144 that it is received as 010. So using P as a symbol for the chance of transmitting a 1 but receiving as a 0, and Q as the chance of transmitting a 0 but receiving as a 1, express the chances of receiving a transmitted 110 as 110, 101, 011, and 010, which are exactly the 4 things that were mentioned earlier, respectively. For example, express the chances of receiving as 010 as the probability, PR, and then 010. So this way I can tell which equation is for which probability. Then express how to resolve the terms P and Q. In other words, how can you find out the actual value of P and Q? There's no need to actually find the terms. In other words, you don't have to give me the numerical answers, but you have to express P and Q in a way that can be directly resolvable, which means P on one side and then a whole bunch of just constants on the other side. Okay, so given that is what the question is asking, so the first thing we want to do is to figure out, okay, there are two distinct parts to this particular question. So the first part is to express the probabilities using P and Q. So what I'm going to do here is, okay, I'll save the document as a different document, and then I'll make the other one I can do this. Okay, so I'll make a copy first. I'll call this answer. And then what I'll do is I'm going to make a shared folder. I've done this one with my other class already, just not with this class yet. So let me go to 14, 16. And in here, I'll make a folder that is shared. Okay. I'll still need to send you guys the link to it, but once I share this folder, okay, so I'll make it so that anyone with a link to it. So this way you don't have to sign into the apps.lostreels.edu in order to use it. And I'll copy this link, go back to Moodle, find myself a Moodle link somewhere, or just here, sign in. Because this way you can follow along with me, and also you can refer to earlier parts of the document during class. So that can be helpful. Okay, go to 440. And I'll just add a link to the very first part of the class website. So this way you guys can refer to the document a lot easier. Okay, around. Share folder on Drive. Use the link. Click Save and Return to Course. So it should be visible to you now. At the very top part of the class website, the bottom item of the top part of the website, there should be shared folder on Google Drive. So now I just have to go back to the document itself and move it into that folder. So go here, move to, and move this item to my drive, 440, 16 fall, exam 2 shared. Here we go. So for those of you who are using a computer or using a tablet or whatever, it should be visible by now. So with this as a second document, I can now remove all the lines because it's not going to be helpful to me when I do all the editing in class. Okay. And I remove one.
Page break.
Yeah, remove one too many characters. So put a page break back in. All right. So now we can start to actually use this to display the answer as well. So we wanted to show the chances of receiving each particular pattern. Okay, so turn off boldface. So PR110 is going to be the probability of 1 minus P, because P is representing the chances of a 1 transmitted but received at a 0. But since I transmitted 110 and I'm receiving 110, there's no error in this case. Okay, everything was received correctly. Times 1 minus Q, because Q is representing the probability of transmitting a 0 but received as a 1. And the next one is, oops, I take it back. It's 1 minus P again because there are 2 1s and then 1 0, which is 1 minus Q. So are there any questions about how I got this part? PR, the probability of receiving 110 is 1 minus P times 1 minus P times 1 minus Q. Okay, no questions? If you do have questions, let me know. Okay. The next one is 101. Okay. So with 101, I have 2 bits of errors. The first one is received correctly. The second one is received incorrectly, and then the last one is also received incorrectly. The next one is 011, and this one is kind of the same thing, except the first bit is received incorrectly, the second bit is received correctly, and then the third bit is also received incorrectly. And then the last one is PR010, and in this case, we only have 1 bit that is transmitted incorrectly. it will be the first one, so we have a P here. And then the second one is received correctly. The last one is received correctly as well. So we have P times 1 minus P times 1 minus Q. Is that okay? All right. So that answers the first part of the question. Okay, the first part is to express the chances using these terms here, P and Q, and also 1 minus those things. All right, so the next question is, or the second part of this question, is to derive some kind of equation or formulae so that I can resolve the actual value of P and Q. Okay, so when you look at this, we have 4 equations. Okay, these are actual equations because I gave you the exact numbers of each one. In other words, the first one is known to be 0.576. The second one is known to be 0.016 and 0.016. And then the last one is 0.144. Now this is actually, kind of a big. It was a big fat lie when I said I gave you 4 equations, because if you look at these equations carefully, the 2 in the middle are exactly the same, because once you use the commutative property of multiplication and you move the P of the second equation to right between 1 minus P and Q, it becomes identical to the first one. So you really only have 3 equations. But still, with 3 equations and 2 unknown, they are definitely resolvable. Okay? Because you only need 2 equations to resolve 2 unknowns. Okay? All right. So getting back to this is basically a matter of algebra now. Okay? So the basic matter of algebra is, okay, which one do you resolve first? Which one seems to be the easiest to resolve? Yep.
To resolve the probability of 0, 1, 1 and probability of 0, 1, 0, you can divide them and figure out what Q is. But
okay. What about between the first and the last? In other words, I look at this one and I look at the last one, because they are almost identical except for one has 1 minus P, the other one has just P.
Yeah. The PR 0, 1, 1 and PR 0, 1, 0 are almost identical, except one has Q and one has 1 minus Q, but that's okay too.
Yeah, exactly.
It's all the same.
They resolve the same way. So what you do is then you say
144 divided by 16 is easier than 576 divided by 144. It's just a bias.
You're looking at the ratio. Okay, you're looking at the ratio of the constants versus the ratio of the symbolic part. Okay, so I'm going to put the actual equation. Okay, and it really helps to magnify, because the equations is not going to show very well when we have it zoomed out. Okay, so here's the equation. Oh, okay, it needs to be clicked first. Okay, so we are looking at 2 fractions. Okay, the first fraction is the first one, the probability of 110. Okay, I can make this whole thing divided by the probability of receiving as 010, because they're only off by 1 bit. And there are other alternatives as well. I'm just picking this one as an example. Okay. Click. Okay. I'm trying to find out how to put the equation right after the fraction. Oh, there we go. So that equals to, using the symbolic portion, okay, so we have fractions again, 1 minus P times 1 minus P times 1 minus Q as the numerator, and then as the denominator we have P times 1 minus P times 1 minus Q. But we also know that this is, as a value, it is known as, oops, oh, that is not good. So as a value, we also know, that this is just the fraction between 0.576 and 0.144. Okay, is this part okay? Are there any questions about how I established the equality? Is that okay? All right. So now you can simplify this, okay? And I'm going to use the next line here to do this part. This is actually harder than using MathJax, using the LaTeX representation. This is actually harder for me to enter, stuff that I need to enter. So basically the top becomes like this, okay? Because once we cancel out the 1 minus p times 1 minus q, then I only have 1 minus p left as the numerator, and then the denominator only has p left. And then this, I keep pressing the wrong key, okay? And then this equals 2, and then the other part is really just the ratio, the same thing, okay? So I'm just going to copy it from above. So 0.576 and 0.144. So once we have this, it becomes, I wouldn't say exactly trivial, but it is easy to resolve it, okay? So as far as your assignment or your answer is concerned, getting to this point won't give you all the points, so you have to take it one more step so that you end up with this. Okay, so insert equations. So we basically have to say, on one side we have 1 minus p times let's see, 144, and then on the other side we have 0.376 times p, and then the next step is to resolve this one. And one more step and we're all done, okay? So to resolve this, we are moving all the coefficients of p on one side and then the constants to the other side. So now we have p equals 2, and I'm using a fraction here. The top part is going to be the 0.144, and then the bottom part is going to be let's see. So okay, so it's going to be 0.144 plus 0.376. I think that is correct, because we are leaving the constants on one side, so we are moving the. So let's say we put the minus 0.144p. We basically add 0.144p to both sides, so that becomes this number, which is associated with the p. That's the coefficient to multiply the p. And then the other side has a single 0.144 left, and that's why we have to divide the 0.144 by the sum of 0.144 and 0.576. So if you get to this point, that's good. Okay, you don't have to actually put it into a calculator to find out what it is. I think that amounts to 80% or 20%. Pretty sure it picks some fairly even numbers. Yep.
I kind of did things opposite, and I treated P and Q as the probability that they would be correct, as opposed to that they'd be wrong.
But then you didn't read the question carefully. Okay, so I will take points off because of that. But as long as you still show that you know how to derive the equations and figure out the answers, I will still give you your partial credit for that. All right, so now that we know what is P, how do we resolve for Q? Yep, just plugging in, right? So plugging in, if once you know all the P's, P is really just this number. You don't have to resolve this number. You can even call this X, okay? Call this number X and then plug it into the second equation, or any one of these equations will do, because they all involve only one Q. But the second one has this one has a particular unique appeal to it, because Q is already all by itself with no coefficients. So that means all you have to do is to plug it in. Okay, I'll just finish this whole thing. Okay. So once we know P, then we know the Q. Okay, insert equation. So Q, using the second equation, okay, the second and the third are basically the same thing. So Q becomes the fraction of 0.016 divided by, in this case, P times 1 minus P. But because P is already known, you just have to substitute the values of P, and you're done. So once you show me that you can resolve P to a particular number, it is okay to say that Q equals to 0.016 divided by P times 1 minus P. That would be fine. Not a problem. Is that okay? Are there any questions about the answer to this question? Yep.
I don't understand how 1 minus p is the probability of getting it correct.
Because p is the probability of getting the incorrect answer or receiving incorrectly.
Mm-hmm.
So the other part of the probability has to be receiving it correctly.
So if you put a number to it and say there's a 60% chance that a 1 is going to turn into a 0, then it's a 40% chance that the 1 is going to be a 1.
Okay.
Which is the 60 minus 1 minus 60.
Yep.
Equals 0.6.
Yep. Because the probabilities all have to add up to exactly 1. Yep.
I didn't do it exactly that way. I was able to, or I expanded out all of the equations there. So I was able to insert equation 3 into equation 4 and get a quadratic equation from that.
That's fine too. Not
right.
a problem.
All
It
right.
doesn't have to be exactly this way. It's just this is one of many ways to do it.
All right.
As another student pointed out, you can resolve for Q first. Okay.
Yeah.
So
All
there
right.
are many ways to do this. So what I'm really looking for is just one, this part is important. Okay. This part is really important because once you see this part, then you have many ways to resolve the actual values.
Okay.
Okay. You can use quadratic. You can add up the numbers. You can divide and use the ratio. There are tons of ways to do
The
it.
second and third equation are actually the same.
They are the same. Yep.
Yeah.
But that's intentional.
I thought that was a nice touch.
Thank you. All right, so that's the answer to question number 1. Are there any questions about number 1 before we move on to number 2? Okay, no questions. We are going to move on to question number 2. So I'll do exactly the same thing. I'll go ahead and delete all these lines, which is basically there to help you write your answers. I don't know whether these lines are too dense or not. Were the lines too dense? I mean, to fit your handwriting, or was it just about right?
Just right.
Just about right? Okay. As a college student, I bought wide rule binder paper because I can fit 2 lines of my handwriting into one single line. And I have to divide, I have a center line to divide my paper into 2 halves because, my handwriting is so small, I can never really fit one, I cannot use an entire line. So when I chop it into 2 halves, that's a better utilization of the area on the page. That's why I'm not a good person to gauge how much space your handwriting needs. Okay, so the second one is, I would say, pretty similar to the practice question number 2. Okay, except this time I'm using close to exponential to the power of something, except there's a -1 at the end of it, but it still works. Okay, the first time we saw something like this was when we analyzed the time complexity of the binary search algorithm. The problem size in the spreadsheet goes from 1 to 3, and then from 3 to 7, and then from 7 to 15, and so on. So when I use the spreadsheet formula to come up with these numbers, that's exactly what I used. So that was basically the first time that we actually saw these numbers in use, but I'm just reusing that concept here and cast it as a proof problem. Okay. So to finish the proof, the first thing we need to do, because this is proof by induction, we have 2 distinct steps. Okay. So the step 1 is the base case. In this case, the base case is pretty much spelled out. Okay. So the base case is saying, okay, f of 0. Okay. So let me insert equation. F of 0 is 0 by definition. Okay. That's not a big deal. But does the theorem work on the base case? Because if the theorem does not apply to the base case, then there's nothing to prove, because the base case becomes a counterexample to the theorem, and hence the theorem has to be false. There's no other way to do it. So we have to show that the theorem does work for the base case. In other words, we have to then ask this question, okay? is this, okay, 2 to the power of 0 minus 1? Okay, in other words, my question is this equality holding? And the answer is yes, okay? It does hold because 2 to the power of 0 is 1, 1 minus 1 is in fact 0. So I established the equality on the right-hand side, which is what I'm highlighting on the projector right now. And the other part is by definition. So this part I don't have to prove because by definition f of 0 is 0. So in the end, okay, I can now establish the equality is between f of 0 and what I claim to be true for all the elements from the domain, which is f of x equals to 2 to the power of x minus 1. So that means the base case is proven. Okay. Okay, so if I want to be extra tedious, I can now claim the following. So I can now claim and say that the theorem applies to f of 0. Okay. All right, so that's step 1. Step 2 is the induction step. The induction step basically says, let's assume the theorem works all the way up to a particular number k, and using that assumption, how can we prove that it also works for k plus 1? Okay, so let me just spell out all these terms. Assume the theorem is true for x equals k. Prove that it also works. The theorem, okay, let's make it very clear. The theorem is also true for x equals k plus 1. So that's the induction step, okay? All right, so let's see how we can do this. The one thing I don't like about Google document equation is it doesn't let me enter multi-line equations. It's only one line or one little chunk at a time. And there's no hotkey to get to insert equation either. As far as I know, there's no way to do it. Does anyone know any hotkey to? No? Okay. I don't even know there are any ways to program hotkeys into Google document. Okay, so we'll just have to do it the long way. Okay, so we are basically looking at k plus 1 as a case. So the first thing we notice about f of k plus 1 is, let's just go by the definition. Okay, so if I go by the definition, I know it is 2 times f to the f of k plus 1. Okay, because that one is just based on the definition, the recursive definition of f. Is that part okay? Okay. So now the next line, this is getting rather tedious, right? Okay. So the second line is saying, f of k. I think we know something about f of k according to our assumption, right? So according to our assumption, the theorem is true for x equals to k, which means f of k is 2 to the power of k minus 1. Okay, so let's go ahead and write that down. Okay, so we know this is 2 to the power of k minus 1 plus 1, and then we are electing 1, 2 on the outside here. Okay, so the only difference between these two lines is f of k using the assumption of the induction step is now expanded to 2 to the power of k minus 1. And the rest of this is really nothing more than just simple algebra. Because now we have 2 times 2 to the power of k, so so it becomes 2 to the power of k plus 1. K plus 1. And then we have a minus 2 and then the plus 1 here, right? And then you can obviously combine the minus 2 plus 1 to just minus 1. So now we end with 2 to the power of k plus 1 minus 1. And that's the end of the proof, because that's where we want it, right? We want to establish that f of k plus 1 is 2 to the power of k plus 1, which is the stuff that is inside the parentheses, minus 1. Yep.
Right there, I plugged in x for k plus 1.
Say again?
Because k plus 1 is x, so it's 2 to the x minus 1.
Yep, exactly.
Okay.
Yep. But if you show up to this step, show as much as I have shown on the projector, that's sufficient as a 100% correct answer. Yep.
I was wondering though, do you have to plug in X or is that okay? Is that just
No, this is okay.
okay?
Yeah, because all we are showing is this is the same thing as saying okay, f of x is 2 to the power of x minus 1 when x equals to k plus 1. It's basically saying the same thing.
Okay.
Yeah. All right. Any questions about number 2? Question number 2. And you can, yeah, go ahead.
So your answer has to have a K in it?
My answer still has a K in it because the proof that I need to finish is to prove that the theorem is true when x equals to k plus 1 in the equation. But x is really just referring to the domain of the function. So if I use k plus 1 explicitly inside of parentheses after f, it serves the same purpose.
I used X plus 1.
X plus 1 is fine as long as you're consistent with the whole thing. With it. Okay? Because the key here is to first use the definition of the function itself, the recursive part of the definition, and then the second part is to use the assumption of the induction step, which turns f of k, or f of x if you will, into 2 to the power of k minus 1 or 2 to the power of x minus 1. So as long as you use x consistently, it's fine. Not a problem. Is that okay? Question number 3. Okay, once again we get back to the casino. This time something else happened. So in this particular question, a secret observer, because the casino can throw people out if they see that these people are actually observing and recording. So a secret observer went to a casino and observed that there were 213 sequences of 5 tosses that somehow end up with 2 heads and 3 tails, where the ordering is not important. So you can have head, tail, tail, okay, or you can have tail, head, tail. It will all be lumped into these 213. Okay. Unfortunately, one cocktail too many. The observer lost the frequencies of all of the other observations, except there was a total of 680 sequences. Okay, somebody kept track, of the entire, night, and they say, okay, well, there were exactly 680 sequences. So of course, but the first question is it still possible to figure out whether the coin is fair or not? Okay, so let's handle the first one first. And it says here, explain your answer of what information is still available to make this possible. Okay, what do you think? Why is it possible, first of all?
Yeah.
Yes. Okay. So what information are you going to use to make it, so that you know it's possible?
The number of 2 heads, 3 tails sequences.
So we know the expected frequency of observing 2 heads, 3 tails because of the binomial equation, right? Because of the binomial theorem. Okay. So that's basically the answer of the first part. So the first part doesn't need any actual equation. Okay, so let me delete all the lines and then give you the write-up here. Okay. There we go. Okay. So for the first part, we say it is still possible to assess whether the coin is fair because we know the expected frequency of observing 2 heads, 3 tails based on the total number of observations. Okay. So that's all I expected from the first one, simply to say that yes, it is possible because we know the expected frequencies. So the second part is saying, okay, I think the second part kind of hints that the first one is saying yes, there's a way to do it, because otherwise there wouldn't be like a second part and it's long like that. So the second part says if it is possible, how do you assess whether the coin is fair? you don't have to compute the values. You just have to tell me what computations you're going to go through and what comparison are you going to use to say, okay, if blah 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 blah, then there's good reason to think that the coin is fair. If that condition is failing, okay, then the coin is probably not fair. Okay, so what are you going to use? That's the question. By using the binomial theorem, okay, very good. So let's say we use the binomial theorem. Okay, what is the binomial theorem telling you? Okay, so what it's telling you is something like this. Okay, let me insert the equation. Okay, so in this case, we're going to say P is the probability of observing a head, Q is the probability of observing a tail. Okay, we kind of use this term in class as well. Okay, so now we can say P plus Q to the power of 5, because we have sequences of 5, right? Okay, and it equals to P itself to the power of 5. Oops. Okay, I keep using the wrong key. Okay, I keep pressing the backspace button when I wanted to press the plus button. Okay, so I'm not sure whether this will work or not. We'll give it a try. So the next one is 5 choose. Oh, it does work. Oh, but it doesn't do the choose as a, it wants to say choose and then type in the 5 and the bottom number, which is 1 in this case. Sorry?
Prefix.
Yeah, it's a prefix notation instead of an infix notation in LaTeX. Okay, so this one is P to the power of 4 Q, like that, right? And then the next one, if you do not spell out the entire thing, I'm not going to take any points off, but you do have to get to the one that we care about. Okay, so in this case we have P to the power of 3, Q to the power of 2, to the power of 2. There we go. And then we can copy, paste. Okay. So the next one up is going to be 5 choose 3, P to the power of 2, and Q to the power of 3. And then we have 5 choose 4, P to the power of 1, Q to the power of 4. And then the last one is just Q to the power of 5. There we go. Okay. So how is this going to help us? Well, the one that we need is 2 head and 3 tails, right? So 2 head and 3 tails is this particular one, right? Okay. So we pick out this particular one and say that, okay, this is representing the probability of observing 2 heads and 3 tails, order not being important. Okay, that's the entire probability. Okay. So now we can say, okay, so the probability of observing 2 head, 3 tails, regardless of whether the coin is loaded, is the following. Okay, and just pick out that one thing. Okay, so you just say PR. You don't have to spell out exactly the way that I do, but this is the reasoning of why it works. So we say insert equation, and I just pick out the one that I need here. So I'll pick out this thing, copy, paste. There we go. Is that okay? But do we know the observed probability? We do, okay? So the observed probability is the frequency, the ratio of the frequency. I think it's 213 on the top, and 680 as the bottom. Okay. Okay. Which basically means we now know that meaning that Now this part is, we haven't really talked about this part, so I'm just going to say, it is like that, but there's a big number theory behind all of this. Basically it's saying, the more observations you complete, the closer your average is going to be to the actual real number, So the more observations that we do, then this quote-unquote equality holds. If I only observe like 2 sequences of 5 tosses, whatever the result is not representative because we don't have enough samples. But the more samples you make, then the closer the observed frequency ratio is to the actual expected probability. Okay, but in this particular case, since we haven't really talked about the large number theory, we'll just say that, yep, that's what we're assuming, because otherwise there's no way to proceed with this particular question. Okay, so now that we have this number here, and we know one of them can be derived from the other one, right? So we can say that this one, the Q here, is really just 1 minus P. Because in a coin toss, it's either head or tail. So once we know the probability of landing on the head, then the probability of landing on the tail is 1 minus P, which is what we call Q here. Is that okay? So given this, it is actually resolvable. Okay, you're not required to actually resolve the number, but it is resolvable. And so once you resolve this P, how would you assess whether the coin is loaded or not, or whether it's fair? Yep.
At this point, what I did is I put in 0.5 for the P and the Q, and I said that the 213 over 680 should equal what you would get with when you multiply.
Yep, that works too. Plug it in, because I just need to know whether it is fair or not, right? So you plug in 0.5 into P, you can figure out this number. If the equality is pretty close, then you say, well, I guess it's close enough. If it's way off, then you go like, I don't think the coin is fair. Yep.
Couldn't you from now you could turn your 5 Q's 3 times P squared times 1 minus P cubed. You can say in 680 observations, if the probability were 1/2, what is the probability that you'll get less than or equal to 213 observations? You can figure out what the mean is, and then you can figure out the standard deviation of that value, and then you can say, okay, what's the probability that after we do this many trials, it differs from the mean by this much.
You can do that, but we haven't talked about the Gaussian distribution in this class.
You don't need the Gaussian distribution. You just use the distribution. You can use the actual distribution. I just said that the Gaussian distribution would be a good approximation.
Yep.
To the real distribution.
Yep, but as far as the answer of this question is concerned, you can just say, okay, if I plug in, you can go 2 routes, okay? You can say, okay, I can resolve P, okay, because in this case P is relatively easy to resolve. So you can either resolve P and figure out whether P is close to 0.5 or not, or you can plug in 0.5, saying that let's assume the coin is not loaded, it is fair. Is the number on the right-hand side close to the ratio of the frequencies that I observed? If it's close, if one is 214 divided by 680 and the other one is 213 divided by 680, it's close enough. On the other hand, if it's 100 divided by 680 on one side and 213 divided by 680 on the other side, then it's different. Okay, then you have reason to suspect the coin is loaded. Is that okay? That's what I'm looking for. Yep.
What if I got all of that, but then I made a different ratio on the right-hand side?
What ratio did you use?
I divided that by 100 because I thought it'd be, I don't know what I was thinking. 100.
You probably have some points taken off,
Yeah.
but as long as you can still use this part here, it will still a partial credit.
Okay.
Yeah. And this part, by the way, you can also change this 3 to a 2, because 5 choose 3 is the same as a 5 choose 2. All right. So are there any questions about number 3? Question number 3, It's all good? Okay. Moving on to the last one, which is actually one of my favorite questions. And did anyone take CISP 300 from me? Okay. Do you remember that? No? Okay, very good, because then other students cannot say that you have an unfair advantage of taking CISP 300 from me, because we actually did this in 300 as well.
Okay.
Okay, so let's go ahead and work on this one. Okay, let me once again get rid of all the, oh, this one has an entire page of empty lines. Okay, so let's go ahead and talk about the question itself. So the first the question is starting with any algorithm to test whether a number is prime or not. Okay, how do you test it? In other words, okay, the best way to illustrate it is to use a spreadsheet to do it. So I'm going to say a new spreadsheet, and then I'll pick myself a pretty big number and say, okay, let's check out whether this number is prime or not. Okay, so we'll pick out, okay, let's see, is that number clearly divisible by 3 or not? It's not, the sum of these digits does not seem to be divisible by 3. So we can use this number, okay? If this turns out to be a non-prime number, we'll keep adding stuff to it until it is, okay? So I'm asking the question, is this number prime or not? So other than looking up a huge table of all known prime numbers, you really don't have a whole lot of choice but to test it, okay, to figure out whether it is prime or not. So this is exactly what we're going to do here, okay? So I'm going to use the equation using the modulo operator. I can now say, let's figure out the modulo of A1, and I have to be careful with $1 because I don't want the row number to change as I make copies of this formula, with the first number, which is a 2. And there are different ways to deal with a 2. I'm just going to use, okay, I'll just put a 2 here, okay? And the remainder of this division is 1, so it is not divisible by 2. Most of you will say, Tech, we already know way ahead of you that this number is not an even number because the least significant digit is not an even number itself. But if you are using an algorithm, okay, having these special cases of if this is an even number, it's not going to be a prime number, those special cases is not going to help, okay? It's only helpful when you're dealing with it using the eyeball algorithm, which is what we use for the most part, okay? So that's not going to be useful. So this 2, I can now say that, okay, instead of using 2, we'll just use the row number. So in a spreadsheet, you can use row with open and close parentheses to refer to the row number of that cell, okay? Works out the same way. And now I can ask, okay, how about division by 3? It has a remainder of 3. Division by 4, it has a remainder of 3. And I can keep going like this, okay? And you can say, but why do you even bother to divide it by 4? Because I don't have a table of prime numbers, okay? So if I don't have a table of prime numbers, if I want to skip the composite numbers, that by itself is more work. So I might as well just retest it with even composite numbers, even though it sounds stupid, it's actually not too bad, okay? But this allows me to keep dragging this thing down until I find a 0, okay? Or if I cannot find a 0, when do I stop? That's the question, okay? When do I stop if I cannot find a 0 here? So far, I still have not found a 0. Okay, so I can keep going. And keep going. So the question is, do I need to go all the way to this number itself? Because the number has to be divisible by itself, right? So when I divide this number by itself, it has a remainder of 0. Yep.
Is this going to be in the shared folder?
I can certainly save it and put it into the share folder. Yep, go ahead.
So you just go to the square root of that number, right?
Right. The theory is I only have to go to the square root. Any test past the square root of this number is not going to give me anything useful. So that's the whole point. But let me put it into my shared folder first, because I do want you guys to kind of be able to access this file, even though it is unlikely to be used again in the final exam.
I just think it's cool the way you use the spreadsheet.
Oh, you haven't seen how I really use a spreadsheet yet. And we're going to rename it, okay, to say find prime, determine. Right. There we go. Okay, so let's figure out what is the square root. Okay, the square root of this number is 200 something. Fine. Okay, so we'll go ahead and get ourselves all the way up there. Make sure that we don't have any zeros in between, right? Okay, I don't see a zero here. Nope, nothing yet. No zeros. What was it again? 200 something?
270,
280.
280
Okay. The chances of actually picking a number that is prime is lower and lower as the number gets larger. It makes perfect sense, right? I mean, because you have more and more factors. Yeah. Okay, I think we went past that point. Okay, so it's basically saying, beyond a certain point, beyond the square root of the number itself. Okay, so if you look at the row number, those are the potential factors that I'm trying to use. So beyond a certain point, I can keep going, but I'm not going to find any factors because I have not found anything by the time I get up to the root of the number. Okay, but it seems to make sense in a way. Okay, because if you look at all the numbers that we have dealt with, like normal, usual numbers. Okay, so let's look at 14. How can I write 14 as a product of two integers? Well, the first one is 1 times 14. One of these numbers is less than or equal to the square root of 14, which is 3 point something, right? Okay. I can write 14 as 2 times 7. 2 is less than or equal to 3 point something. Okay. Let's pick something that's tricky. How about 9? 9 is written as 1 times 9. 1 is less than the square root of 9. Okay. But 9 can also be written as 3 times 3. 3 is less than or equal to 3, which is the square root of the number. So the theorem seems to hold true no matter which integer we choose and write it out as a composite of, or as a product of two numbers, two integers. Is that okay? So that's the point of this particular theorem, is we can stop pretty early. We don't have to go all the way to 70-something thousand, in order to stop. We can stop at 200-something. Is that okay? All right. All right, switching back to the question itself, okay? So the theorem that we are using is this one. Okay, so I'm just going to highlight the theorem and then talk about it a little bit. So the theorem is basically saying, okay, go ahead and pick any three numbers, okay, x, y, and p as a natural number. Okay, n is the set of all the natural numbers, starting with 0, because I have heard that some people say that natural numbers start with 1, so I just want to make sure it is clear that we're starting with 0. Starting with 1 wouldn't bother this theorem at all. Okay, it will still work. Okay, so once we pick out three numbers, okay, they can be the same, they can be different, they can all be one particular value. It doesn't really matter, because the theorem, or the inside of the quantifier, it's saying, okay, we really only care when p is the product of x and y. Because when p is not the product of x and y, the entire thing is true anyway. The implication itself is true. Does that make any sense? Because in the implication, if the first part is false, then the entire implication is automatically true. So the only real question is, what if p is actually the product of x and y? Well, if that is the case, if the first part of an implication is true, then the truthfulness of the entire implication now depends solely on the second part. The second part is a disjunction. The B is a disjunction. And it's saying x squared has to be less than or equal to p, or y squared has to be less than or equal to p. If you prefer, you can always say x is less than or equal to the square root of p, or y is less than or equal to the square root of p. Okay, I use the square because it is actually easier to do the proof later on. Is that okay? All right, okay. Okay, and I want you to prove this by contradiction. And I already know that some of you may have forgotten some of the quantifier stuff. So I gave you a hint here and say that, okay, if you have to negate something that is for all, okay, you turn it into a there exists, but then you have to negate the inside of the quantifier. So the negation outside of the for all moves into the inside of the there exists. Okay, just in case somebody forgets. Okay, intuitively it makes sense. Okay, it is not the case that everyone is a Trump supporter. It's saying the same thing as there exists someone who is not a Trump supporter. I'm not saying whether I support Trump or not, so I'm not violating any rules of this campus. Is that okay? Making any sense? Okay. So it's really just a symbolic way of saying exactly the same thing. The negation of the for all means that you can use a there exists that is non-negated, but then you have to negate the predicate itself so that you can basically state exactly the same thing. Is that okay? And then the second clue is you also have to be able to use the negation of an implication. Okay, the reason why you have to use the negation of the implication is what we are doing is we're negating this whole thing, because the negation of the theorem is the negating. We are basically saying it is not true that for all x, y, p, blah 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 blah. But since I gave you a way to put the negation of outside the for all into the inside of the there exists, so that means whatever is inside here, okay, becomes a negation. But that is an implication itself. So you have to negate the implication. Okay. So given all of these things, let's see how we can negate the theorem. Okay, so step one of proof by contradiction is to state the negation of the theorem. Now this part is really important in this case. In some cases it's not important because the negation of the theorem is very clear and it's intuitive and it's easy to understand. This one is a little bit tricky, so that's why it is important to state the negation of the theorem. Okay, so we'll start with something that is easy. Okay, so we'll start with the original theorem and negate it. So all I'm going to do here is to say, let's say that's not true. Okay? Is that okay? So then the next question is, okay, so if I negate this, what does it really mean? So I paste, put the equal here. So here I start to use some of the stuff that I put up in the question itself as a clue, and I say I'm going to move the negation. I'll move the negation into the inside here, okay, and then I need an extra pair of parentheses here, and I would change the for all into a exists. Is that part okay? I just made use of a clue that I put into the question itself. Okay, all right. Then I have to say, well, that seems to be useful in a way, but how am I actually going to make use of this? Okay, I put a parenthesis, close parenthesis at the wrong place. Okay, so we'll take a look at this one and say, okay, so now we have the negation of an implication to deal with. So then you have to kind of think about, okay, so how do we deal with the negation of an implication? How do we do this so that we end up with just the usual conjunction and disjunction thing instead of the implication? Okay. So I'm going to go here and say, okay, let's take a look at this one here. Let's expand this one and see if we can express this in a slightly more intuitive way. Okay. So we say this is the same thing as the negation of not A, right, or B. Is that okay? Because A implies B being not A or B is the definition of implication. Okay. And now we have a negation on the outside and an or in the inside. We can now apply De Morgan's law. Okay. So the De Morgan's law is saying, okay, not A and B is the result of, oops, not B. There we go. So you can look at De Morgan's law as, quote unquote, the distribution of the outside negation into the inside. But in addition of distributing the negation, you also have to turn the operator from a or into an and, or an and into an or. So you have to change the operator. And there's only one more step here because I can simplify the double negation into just A and B. Whoop, not B. There we go. Is that okay? Okay, so knowing that the negation of A implies B is A and not B, now we can apply that here as well. So we'll take this whole thing and say, okay, the negation of this particular thing is keeping A by itself, right? Okay, so this part is A, and this is going to be turning into a conjunction, and then B has to be negated. Okay, so we say the negation here. Okay, I think that may not have all the parentheses matched.
You just need to erase one on the end.
Say again?
I think you just need to erase one on the very end.
I think they are actually matching up just fine. I think they're all matched up.
That's just not drawn, right?
I think we have one too many to. No.
Because you added one, when you had the negation, you took it away, right?
Oh, okay. I see. I got you. Where the cursor is important. There we go. Okay.
That's true for all of them.
Hmm?
Above as well, right?
Say it one more time.
That's true for the middle two lines as well.
To get rid
One
of.
extra parenthesis.
Oh, okay. Yeah. One extra close parenthesis. Okay.
Did you post where this document was?
I believe so. Let me check. It is now in shared.
You can find it at the top of the Moodle.
Huh?
Yeah, I'm on Moodle now. I can't find it.
No, those
Is it
ones
in
were
form,
fine.
or where is it?
Let me get to the Moodle page. It should be here at the top of your Moodle page.
Sure, the one you drew.
Yep. And I'm in. I got too many stuff here because some of these are from my class yesterday. There we go. Okay. Okay, so this is the negation of the theorem. This is a good one, okay? Because now we can basically look at this again and say, okay, there's a lot of mumbo jumbo in terms of mathematical symbols, but what does it really mean? It says there exists, okay? There's a way to pick, if the theorem is wrong, okay? There's a way for you to pick three natural numbers, x, y, and p, such that, okay, they're all natural numbers, such that p is the actual product of x and y, and on top of that, it is not true that x squared is less than or equal to p, or y squared is less than or equal to p. So there is an easier way to state this, okay, because we have a negation outside of a disjunction. So let's do De Morgan's law one more time and see if we can make this a little bit easier to understand. Okay, so we copy this and paste it over here, and this time we take care of this or, okay? So we're basically moving, once again, we are distributing the negation, okay, into the inside, and then we are changing the disjunction into a conjunction. So it's a wedge. There we go. Is that okay? Yep, go ahead.
So then now could you say x squared is greater than p?
Yep, absolutely. But I'll keep this line. You don't have to go through the proof, really as step by step as I do, okay? Because you can skip a few steps that are obvious, okay? But I like to show things, not and not skip too many steps in class. Because not less than or equal to is basically saying greater than, right? Okay, so this one, so let's just read this again just to make sure that we know what it really is saying. It says, I can pick three natural numbers, x, y, and p, such that p is the product of x and y, and on top of that, x squared is greater than p, and y squared is also greater than p. Okay? All right, so let's see what kind of bad things we can get to with this thing, okay? Okay, so that's the negation of the theorem. So step 2, show the negation of the theorem leads to contradiction, which means false, okay? So we want to say that, okay, this whole thing, is false, okay? There's no way we can actually do this. But why is it false? Okay.
X, Y, and for P.
Sorry again?
Can you also plug X, Y, in for P?
Yep.
Right, too, and then kind of show that it's.
Yep. So what we'll do here, there are many ways to do it, but this is the way that I usually do this, is to say, okay, so x squared times y squared is what? There are two things, okay? So let's just use the inequalities first. We know that x squared is greater than or equal to 0. We know y squared is greater than or equal to 0. We know p is greater than or equal to 0 because they're all natural numbers, right? So if you know one natural number is greater than the other one, and then another natural number is greater than the same, p in this case, so we can now say that the product of those two is going to be greater than p squared. Is that making any sense? Based on this part of the negation of the theorem. Is that okay? All right. So we know this one is true, but by the first part, we also know, okay, because the first part is saying p does equal to xy, right? So in that case, if you square both sides, what do you get? We also know, okay, insert equation. We also know that p squared is xy, which is x squared y squared. Right? Now, if this seems really wrong to begin with, right? Because, but what we can do now is to say p squared is the connection now, okay? Because we know that x squared y squared is greater than p squared. We also know that x squared y squared equals to p squared. So the actual contradiction is this part here. So the contradiction, an expression that is always false, is the following, okay? We use p squared as a connection, and then we can now say x squared, y squared is greater than itself. Because I'm using p as a connection piece, because on the top, on the first part, we have x squared, y squared is greater than p squared. But what does p squared equal to? It equals to x squared, y squared. A number cannot be greater than itself. Yep.
The way I did it was that if we're using natural numbers, then x squared has to be at least p plus 1.
Say that one more time.
Because we're using natural numbers,
Right.
x squared, in order to be greater than p, must be at least p plus 1.
X squared being greater than p means that x squared is p plus 1.
Has to be at least p plus 1.
Okay.
And because it's at least p plus 1, then p would equal the square root of p plus 1 times the square root of p plus 1.
Okay.
and that'll never be true.
Why is it not going to be true?
Well, how can the square root of a number times plus 1 times the square root of a number plus 1 equal the number?
Well, you have to spell it out, because you basically have to spell out, because in your case, you can use an inequality of one side being 0 and the other side being non-zero. There's an equality, but you have to lay it out.
I can write it on the board if that helps.
Okay, well, okay. When I grade yours, I will have to assess whether it is clearly a contradiction or not, because this is a clear contradiction. The number cannot be greater than itself.
Well, I think if you saw in black and white, you'd be able to see that it's not.
Okay, yeah. So I will have to actually read your proof to make that determination. Yeah, go ahead.
Oh, I was saying that for mine, I just directly put x, y into b.
Yeah.
And then if you divide by x or y on both sides, you show that x is greater than y and y is greater than x.
Yeah,
which
you-
is true, right?
Yeah, there's another way to do it too, because we know that p equals to xy. You can rewrite this part as xy, so it's p times p, then you have p squared greater than p squared. So there are many ways to show there's a contradiction, but the contradiction, regardless, has to do with a number being greater than itself, or 0 equal to something that is clearly non-zero. Those are the actual end result that I'm looking for. But the derivation are worth points. Okay, so that's being able to show the negation of the theorem itself is worth points. Yep, go ahead.
I got the negation of the theorem, but then I did the rest in English and I reasoned it out how you couldn't find two numbers.
As long as I can follow your reasoning, it will still be okay.
All right.
Yep. But I want to show it in actual equation or in mathematical symbols, because that's what I really like you guys to at least get used to. Okay, maybe not using it in your own proofs, but at least be able to understand it in the class. Okay. Any questions about this particular exam? Yep, go ahead.
Yes, because I think the theorem said that the square number has to be less than p. I'm not sure what.
Say that one more time.
When it was saying how it finds the prime number, how you were saying the square root has to be, the greatest factor has to be less than the square root. And you can't find that in the negated theorem. Because the x squared is bigger than you can't find the number.
But the purpose of the negation of the theorem is to show that it is not possible. In other words, you basically have to show that the negation of the theorem leads to a contradiction.
Okay.
Which means you cannot have a number where you can express the number as the product of two factors, and none of the factors is less than or equal to the square root of the number.
Right, that's what I was trying to say.
Yeah.
None of the numbers are less than the square root,
Right.
because it's greater than that.
And that confirms our observation, which is based on here. Now, well, okay, I take it back. It doesn't confirm our observation because I only claim that if I keep going like this, we're still not going to find a factor. Okay, but to really use this as a quote-unquote example of the theorem, you would have to extend this all the way up to 78,000 something, and see that none of those numbers is a factor. Then it's a confirmation that at least for this particular number, the theorem holds. Okay, but it's one way to observe it. I mean, this is a much more visual way of looking at the theorem, because it's saying, oh, can we stop now? And the answer is yes, we can stop because we are now past the square root of 78,000 something.
Right.
And we can stop now and make a conclusion and say that tech is super lucky by picking a number that turns out to be prime, because the chances of picking a number that is prime is actually fairly small by the time you get to that kind of a magnitude.
1 over log of the number you go to. Like, if you pick a number from 1 to n to be prime, then the probability of picking a prime is going to be approximately 1 over the natural log of n.
Yep. Okay, so here's the kind of since we got 5 more minutes to go, and you actually commute here today, so I don't want to waste your 5 minutes of class time. Why do we care about prime numbers?
Passwords for
Really good at
our
security, right?
It relates to computer security. How does it relate to computer security?
encryption.
Encryption. Okay, very good. What kind of encryption are we talking about? key
RSA key.
pair encryption. Okay? So does anyone know what is key pair encryption? What does it do? Why is it kind of cool? Come on.
One side has a public key, the other side has a private key.
You pick which one is public and which one is private. It doesn't really matter. So the whole idea of key pair encryption, I only have, well, let me make it very distinct here. Here we go. Okay, so let's say we have key pair encryption here, and I'll make it even better. So this one with a big old keychain is my private key, okay, because the keychain is actually my pepper spray. So we'll make it my private key because I carry it with me all the time. And this one with a tile is my public key, okay? So I can have a tile so I can ring it, so I can find it, okay? Okay, so the idea is if I use the public key to lock something, let's say we have a magical lockbox corresponding to key pair encryption. If I lock that lockbox using the public key, I can leave the public key on the ground, make 20,000 copies of that, and sprinkle it all around the campus. But because I lock it with a public key, it cannot be unlocked using the public key. If I lock it with a public key, I can only unlock it using the private key. If I lock it with a private key, then it can be unlocked using the public key. That's key pair encryption. Yep.
I heard that a good example is that the public key is just kind of a lock, and you can make as many locks as you want, as many padlocks as you want, but you're the one who has the key. So the way that you communicate with people securely is you send them, you go and have them send you a box that's locked with their lock, and then you put it on your own lock, you send it back with 2 locks, they unlock their lock, and then they send you back the box that's locked with your lock, and you open it with your key.
Well, I'm not sure about that part, but I do know one thing, okay? These 2 keys, okay, they are made with special prime numbers, okay? The relationship between these 2 prime numbers is special so that we can use the key pair encryption method. So why do we care about big prime numbers? Because if you have a way to generate and test really big prime numbers really efficiently, you can break this kind of encryption really efficiently as well. And that's why it's a big deal. Okay, how fast can we find and confirm numbers at a prime is a big deal. Okay, because we are looking for prime numbers that are really huge. Okay, when it comes to encryptions, and that envelope is always changing. Do you guys still remember in the early days of Wi-Fi we had 802.11b, and the encryption standard at that time was called WEP, or Wire Equivalent Protection, which by today's standard is no protection, right? Mm-hmm. Why is it no protection anymore?
It's pretty easy to break.
It's easy to break because people can observe the traffic and be able to reverse engineer the actual encryption key itself. So the same thing applies to key pair encryption, because with the increase of computation power, the ability to come up with these prime numbers is also increasing. Yep?
Don't they use semi-prime numbers?
Semi-prime numbers.
I think that's the product of 2 prime numbers. I think that's what it is.
Yes, it is based on 2 prime numbers, and the product has special properties.
Mm-hmm. And those are even harder to find.
Those are hard to find as well. Yep. But nonetheless, okay, prime numbers play a very important role in computer security, especially in encryption.
Really, is it really only because they're hard to find? That's why.
Yes, because they're hard to find and difficult to confirm. Because the chances of finding a prime number when they're large, as he said, is 1 divided by the log of the value of the number. So the larger the number, the more bits that you're talking about, the fewer chances that you can actually find a prime number.
We wrote a program, or Fox wrote one that finds all the prime numbers sequentially, and when it gets to the 100 millions, it starts going really, really slow.
Yep.
You can let it run all day, and it will find. It won't even make a dent into the prime numbers.
Yep.
Quantum computing actually makes the task a lot easier. So once we have everyday quantum computers, we're gonna definitely need to change up our encryption. Of course, it also gives quantum encryption, which